Hello, everyone, and thank you for joining us today. Welcome to ABO's webinar series. Today's topic is electrical safety for cable testing and fault locating. My name is Ron Spatero, and I'm the marketing manager for ABO Training Institute, and I'll be your moderator for today's presentation and supporting you on technical issues or questions for our presenter. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All attendees are eligible to receive one NETA CTD and one professional development hour credit. You will receive your attendance confirmation in an email within 2 business days after the webinar. That email will also include a copy of the PowerPoint presentation and a link to the recorded video of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered after the webinar ends. Our presenter today is Mark Franks, Senior Cable Instructor and Curriculum Advisor at ABO Training Institute. Okay, let's go ahead and get started. Thank you for joining us today, Mark.
Thank you, Ron. Welcome to the webinar, and our topic today is electrical safety during cable fault locating and testing exercises. And today, a lot has been said about electrical safety in the U.S. today, and obviously one of the reasons, if you look at my first bullet, is this is one of OSHA's fatal 4. The fourth single cause for electric fatality or for fatality in the nation is due to electricity. We have serious issues with arc flash burns. Over 2,000 people are admitted annually to major burn treatment centers, and these arc flash incidents are typically in the range of 2 to 4 months of treatment or even more. Most of the electrical accidents that occur after we investigate them find that these could have been prevented if PPE items were utilized or work practices were utilized. Then obviously the incident would not have occurred anyway. That's one reason that training in recognizing and avoiding hazards and how to mitigate them is so important today. Most incidents involving testing and fault locating and cable testing actually involve inadequate verification of power and or issues in lockout tagout. Safety policies and procedures and guidelines are the responsibility of the company, and it's the responsibility of the employee to follow them. In de-energizing and locking out and tagging out seems to be the most important thing in testing and testing maintenance, so emphasis is put on these issues. First aid, CPR, and emergency procedures are also training issues that have to be met, and OSHA requirements for these issues are also for all qualified workers. Here's our agenda. We'll talk about electrical hazard recognition, and we'll discuss electrical protection and electrical protective items. Then we'll visit safe work practices for testing and fault locating, and we'll look very intensely at the test area safety check that has to be done by a qualified technician. Training requirements will be discussed, and also then we'll summarize with some comments that we have about the presentation. OSHA mandates electrical hazards to be conducted in OSHA 29 CFR 1910-132. It's very explicit as to the company's requirement for conducting hazard assessment in the workplace for the tasks that are actually done. In order to assess PPE and provide PPE, the assessment has to be completed. These protective measures need to be employed based on what employees actually do. So in the cable testing and cable fault locating world, we have numerous tasks, very complex pieces of equipment, most of which can create lethal shock. And we need job hazard analysis performed and procedures written to actually perform these types of tasks. We have shock protection available from 500 volts to 3600 volts. And in addition to that, we have arc flash and blast protection also available in various ranges of protection level. OSHA recognizes, and so does general industry, that there are three major categories of electrical hazards, and that's shock, electrical arc, and then blast. If you have an arc flash, typically you have a blast associated with it. We have electrocution from electrical injuries, which would lead to death, electrical shock, which also leads to many injuries, and then also electrical burns. Burns can take more than one course. You can have electrical current burns from within due to current flow inside the body, but you can also have burns that are external from radiation and from possible burning of wearing apparel that got ignited during the arc flash. Another issue, an indirect issue, might be falls. A person working on a ladder and receiving a shock, which might have been minor to start with, turned into a major incident because of the result of a fall. This shows the resistance of the body as far as current path, and if you'll notice, it's about 1,000 ohms hand to hand and approximately 1,000 ohms hand to foot. So in shock type contact injuries, the current flow is normally, if it's a hand to hand contact, it's going through the heart region. There are other paths that also include the heart region, but just 120 volt shock would create, with 1,000 ohm resistance where the person is perspiring or wet, would create about 120 milliamps, which would be lethal shock in most cases. The main issue with shock or current is the burning effect as the current goes through the body. This has to do with the path that the current actually takes, the amount of current flowing, and essentially how long this current's actually going to be flowing. Remember, the longer the current is flowing in the body, the more heating effect that you get, and you get more internal burning as the shock duration increases in time. One of the most common shock-related issues is the issue of burn. Burns are caused from three major types. This is the electrical burn, the arc flash burn, and then the thermal contact burns. So we have a lot of these. When you start analyzing injuries, you'll find that there are thousands of electrical burn injuries annually in the workplace in the U.S. Electrical burns are very detrimental to a person. They result in internal inflammation. You need immediate medical attention with electrical burns. These burns are often very expensive. The average burn treatment in a burn treatment facility runs about about $750,000 a month. These burn injuries normally go into the millions of dollars of loss. Plus, the other issue is, I think the human side of this we have to consider, is that burns are very often disabling and even fatal. Burns to the hands are real common, and this is obviously a contact made to energized parts without any protection, and that usually can result in burns on the hand or non-insulated tools being used during the work, and this can cause burning to the hands. Clothing may catch on fire, and that's one reason in the U.S. we've spent a tremendous amount of effort in trying to ensure that workers that are exposed to flames or electric arcs are wearing non-flammable clothing. This is an example, it's a real good example of what happens when a worker is not wearing the proper clothing. What you're looking at in this picture is the remains of a non-FR rated shirt, and that's the back of the shirt that you're looking at because the entire front of the shirt was burned off the worker. If you'll notice, the gloved hands are burned significantly. The strip down in the middle of this, you see the arrow pointing over to it, that's basically the button strip on the front of the shirt. This is the back of the shirt that we're looking at here. So the entire front of the garment's already gone. Well, you can imagine where most of that went. If that is, and it appears that it was a polyester type garment, most of that was probably melted on the individual skin. The culprit is up here at the top next to the hard hat, the non-insulated screwdriver being used and working on energized equipment, and obviously started the short circuit that caused the real high energy arc flash to occur. The worker may have got out of this with just minimal injuries had he not had on a flammable shirt. Temperatures as high as 35,000 degrees Fahrenheit have been reached in these electric arcs. That's about 4 times the surface temperature of the sun. So it doesn't take long to figure out. If you stand very long in front of that type of intense heat, you're going to get burned. And again, these burns are very costly to the individual, and they're also very costly to the company in dollars. 4 primary hazards associated with arc flashes are the radiation, the intense light. This is ultraviolet light given off by the arc flash during the intense arcing. There is a sound wave produced that can exceed 165 dB. 165 dB on a sudden impact to the ears is going to create all kinds of damage to the eardrums. The arc itself can produce a pressure wave. When you have copper and aluminum melting and going through the melting stage actually to a vapor, its expansion rate is extremely high and it rivals dynamite. The pressure wave generates intense pressure on the equipment, also intense pressure on the individual. 25,000 amp arc, 2 feet away from that, a person's getting about 480 pounds on the front of the body. That may not sound like a lot, but in a couple of cycles, that's a tremendous amount of pressure. So we've reviewed the hazards. We've got shock, arc, and blast type hazards that we're dealing with. In cable testing and cable fault locating, we're connecting to and working in systems that were previously energized. So it's very important that we take the right precautions and apply the right PPE. We're going to talk about personal protective insulation, warning signs, posting warning signs and looking at warning signs on equipment, protective grounding to be used in the test areas, test area guarding. When we're using high voltage and high current test equipment, we want to make sure we're obeying by the manufacturer's instructions and the use of the equipment, the safe use of the equipment. We'll talk a little bit about electrical protective devices that are kind of ancillary to what we're doing, and then other protective items and equipment like flash protection and those types of pieces of equipment. In the PPE world, we have several things to consider, rubber gloves obviously being one of the primary. And these rubber gloves have to be rated, they have to be tested, we have to have an in-service care and use program in the company safe work practices to actually use these. The worker, when they receive gloves, need to demonstrate that they understand how to do the daily inspection. And we're looking for holes, tears, punctures, cuts, or any type of texture change or anything else that appears to be damage in the glove. Scuff marks sometimes can be fairly deep. Gloves need to be inspected before you use them each day, as demonstrated in the picture of the worker doing a simple air test. It's a simple air test. It's a simple inspection just to ensure that the gloves don't have a tear or hole or anything like that in them. Gloves are rated from 500 to 35,000 volts and essentially can be used at whatever rating or level that we're actually working on. Warning signs involved in permanent labeling or fixed labeling out in the test area. We may have warning signs on test equipment. The manufacturers may have placed warning signs there as well. These need to be observed. An example here is danger high voltage testing in progress. Imminent electrical shock is imminent danger. Imminent danger signs typically are red, white, and black. To protect workers in the test area and to ensure that the cable system that we're going to test is actually de-energized, the only way to ensure that is to actually verify it and then short circuit and ground the systems. These PPE grounds need to be rated. They need to be engineered basically to withstand any type of short circuit current or duration of short circuit that might be imposed on them. The grounds need to be installed in a method of equipotential where the worker is not exposed to any separation of potentials in case an accidental activation occurred. Grounds can be removed during testing. It would have to be. If we're testing that cable, we would have to take the grounds off of it, but they need to be put back on once the test on that cable is completed. If grounds are not practical, then we work in an exception where other safe work practices may apply in the use of barriers and other methods of protection. Remember one thing, and this has been around a long time, it's not dead unless it's been grounded properly. Grounds provide maximum safety for personnel because we equalize the voltage in the work site. Other types of issues that are there, like static voltages, induced voltages, capacitive coupled voltages, those types of voltage sources are also diminished or rerouted so that the issues don't create a problem for the worker. The other issue with PPE grounds is to provide a real low impedance path to ground so that we can operate the upstream protected devices as quickly as possible and overall minimize the magnitude and duration of the hazard by quickly de-energizing the system. Remember, when grounds have to operate on an accidental activation, something has already gone wrong with our energy control program because we're energizing a feeder with PPE grounds on it. So they have to do the job. In order to do the job, they have to be sized properly and rated properly and installed properly. These pictures depict the proper procedure or the process for installing grounds. Number one, we have to verify absence of voltage. So we have to test the system that we're going to install PPE grounds on with an approved test device. We pre-test and post-test the tester to make sure it actually works, and we verify absence of potential prior to installing grounds. Inspection of the grounds prior to use is also required, so we would do a visual inspection to ensure that all the fittings are tight, the connections are there, there's no cuts or damage to the cable itself. And then in the installation process, using a hot stick, we would install the grounds. They go on the ground first and then to the phases last. Off, we would take them off in reverse order. But in the ground installation, all of the PPE requirements have to be met in order to adequately install the ground safely at the site that we're going to be testing. The process overall involves verification of the de-energized state, pre- and post-test the voltage detector. These grounds, again, need to be suitably sized and connected to the ground first and the cable or bus last. Only after we properly grounded all the conductors can anything be disconnected for testing. So we want to make sure all the conductors are grounded prior to disconnecting anything to be tested. After testing, then certainly we would reinstall the grounds back. Grounds always go on the ground in first and then come off the phase ends last. Okay, after we have our test area secured, then essentially guarding becomes an issue. We have three basic OSHA requirements for test area guarding, or three methods to apply. One of them is safety signs and tags. If a safety sign or tagging system can work as far as protecting the area, then that would be adequate. Most of the time, these are used in conjunction with each other. You'll have multiple issues being used. We'll have safety signs and then possibly barricades, and could have an attendant as well. This is an ANSI design sign. It does meet the requirements. It says danger. It warns of what is there, hazardous voltage. Gives us an instruction, unqualified persons keep out. In test area guarding, we want to ensure that we keep uninvolved personnel out of the test area or away from the immediate vicinity of the test equipment. Keep in mind that in our test area, we may have exposed live parts, or we may have exposed live parts of the test equipment itself that can actually produce lethal shock. So we need to keep uninvolved, unqualified personnel out of the test area. And most of the time, this is going to require some type of guarding system, either the use of barricades or ropes or simple danger tape works well. Caution tape does not work. Caution tape is, we normally consider that the duck under tape. The danger tape would be danger high voltage keep out. That works real well for most people. The remote end of the cable needs to be secured. If we keep in mind that there are possibly two ends to this cable system, maybe even more, and we need to make sure that we are securing and barricading those areas well, especially if we're going to be energizing that cable with a high current or a high voltage surge type voltage. Post a guard. If we have to, we can put a guard there and just let them guard the entire area and keep people away. And it may be that critical that we have to do that. Keep personnel in the test area to a minimum. Only those who are necessary for operation of the equipment and for safety are necessary to be in the test area as we're testing. If we have other personnel and also people that are in the test area on set of testing, we need to make sure that everyone understands the hazards, everyone understands the voltage levels we're testing at, and they understand the issues, the approach distances and things like that to the parts that we're actually going to have energized. Here's some more examples of guarding, and we can have different types of things. Fences, substation fences have been used sometimes for the test area protection where the fence can be controlled. Partitions, covers, screens, boxes, barrier tape, all of these things are methods that can be used. Basically, we're just trying to isolate the area, give ourselves plenty of room to set up our test equipment safely, and to prohibit unauthorized personnel from actually coming in the test area. Here's some examples of attendant. We have an attendant posted where exposed parts are going to be there. It may be necessary to have an attendant. May have an attendant and barrier tape, that type of situation. The danger tape works well. Most people can use that. It should be installed about waist high and should have the repetitive language, danger high voltage keep out on it. The picture on the right is a little different. This is a picture where the test area is barricaded, but within the test area, there's another area being barricaded. This is a coupler for a partial discharge test set that's in this test area. The corona rings at the top of the coupler become energized, so even with the test area secured, it may be necessary to secure a specific piece of equipment itself, and in this case, of course, barricading was the solution to that. Foot protection. Some of these issues here, the ground fault issues, this is ancillary to testing, but we also need to make sure that we protect our test voltage going to our test equipment. We have protective circuits and methods of using GFCIs and things for that type of testing. So we want to make sure that we're protected even from our supply source. Foot protection, in the electrical world, if you go to 1910, the PPE standard again, 136, you'll find the requirement for electrical workers who are subject to step and touch potentials in their everyday work or in their testing work, certainly, would need EH approved work shoes. These could be or should be hard toe in the case of electrical work. Footwear needs to be maintained, kept dry if at all possible. That's not always possible, but if possible, it should be. Head protection, we're looking at electrically rated hard hats for testing and maintenance. Class E or G would work. Always wear the hat appropriately with the bill forward, the suspension adjusted, and don't store anything up in top like the gloves on the bottom. You can see they're using their hat as a kind of a storage bin. We have other protective items. The daily wear and arc flash suits are very common today in electrical work. Employees have to be trained in the hazards associated with flames or electric arcs. They have to be trained in the levels of protection that they would have available to them, how to use it, and then overall how to mitigate the issues of electric arcs and arc flashes. Employees are prohibited from wearing clothing that, if ignited by an electrical arc, could continue to burn or could cause further injury. And that is a direct 1910-269 OSHA requirement. Arc protection kind of comes in two different categories. We have wear and apparel. We could call that daily wear, and in this case, it's indicating, or we're showing, a flame-resistant, arc-rated flame-resistant wear and apparel being used by the workers. This is wear and apparel. Wear and apparel and PPE are two different things. A PPE level can use wearing apparel as part of that level with the addition of a face shield, a balaclava, and protection for the hands. The individual would have a category of flash protection, but you would have to add those other protective items to it. Arc flash suits, obviously, are rated for the extent of the hazard that's there, and these all levels of flash protection need to be worn with hearing protection. This just shows a makeup of arc protection. It starts on the lower category on the left and goes all the way to the maximum available arc flash capability. Typically, most people wear about the middle of this as their maximum level, depending on the nature of their systems and the actual arc flash issues that they have in the workplace. More safe practices for testing and test equipment. Plan your work. We need to coordinate our work and take advantage of what everyone knows about the project. Everyone knows about the hazards and how to control them. This pre-job discussion is mandated all the way through OSHA and industry consensus standards. It's no different here. For our test technician in charge in the test area, we need to conduct the pre-job discussion before each series of tests. The authority of having jurisdiction over lines and equipment, we may, as a tester, not be responsible for switching and clearing, but certainly responsible for verifying that the system is dead. But whoever is responsible would go through a process of switching, clearing, locking out, tagging out, verifying that the system is de-energized, and possibly installing personal protective grounds as required. It's not a good idea to operate high voltage test equipment in extreme wet conditions. So we need to make sure that we can control the work area, control the environment as much as we can in the work area, so that we're not operating equipment in areas where we're inundated with water. Avoid contact with other pieces of equipment or other lines or bus work or anything like that that's in the work area. We should do a survey of the test site to make sure that we understand what is energized and what is de-energized, and certainly the system that we're working on. Making sure we have adequate power to feed our test equipment is also an issue, and again, the use of GFCIs is a good idea. We'll make sure switches, if we're using switches or ancillary equipment, make sure these pieces of equipment have been inspected. If they're grounded equipment, then we have the third prong, ground prong there available. One of the things to be said here is to make sure we understand the equipment that we're using. High voltage test equipment and high current test equipment may be fairly complex, so test technicians should be trained in the proper use of it, and also to be able to inspect and determine if it's actually functioning properly. If the equipment is determined to be damaged in any way, or the control circuits or anything are not functioning properly, then the equipment should be taken out of service and not used for the test. Keep cords away from heat, oil, sharp objects, making sure we have our test leads, high current leads separated from monitoring leads, those type of things, and all the cords that we're using, which typically we have quite a few in test areas being used to power the equipment itself. In personal protective equipment, just make sure we have the right PPE for the job. Our JHA should give us indications of what we should have. We should have safety glasses, and these should be UV rated non-conductive side rims, foot protection, hard hats, our ART rated wearing apparel and or flash protection as needed, and also follow manufacturer's instructions for cleaning, maintenance, and taking care of PPE items. Other safe practices: the test engineer in charge or test technician in charge is required to inspect the test area prior to each series of tests. And we'll go through that a little more intense in the next few slides. Prior to each series of tests, and we're trying to make sure that all the safety precautions are in place, all the PPE items are in place, the test area is secure, and there are no unqualified or unauthorized personnel in the test area. After completion of the test, the equipment needs to be de-energized and everything should be placed back in an electrical safe work condition. Always meet minimum PPE and safety requirements on customers' premises when performing high voltage and high current testing. All personal protective equipment items have in-service care use programs. These programs dictate that the PPE be inspected properly, be stored properly, be worn properly, and have proper fit. Always wear E or G rated hard hats or head protection, and wear protective equipment for the eyes and face. If there's any danger of arc flashes or flashes from flying objects or anything like that, then certainly we would wear face protection. Face protection may be a face shield, a ultraviolet rated face shield. More safe work practices for testing: high capacity cables, where we have been testing power cables. They're fairly capacitive in nature. If these cables have been tested with high voltage, then probably they retain some of that capacitance or can. So discharging medium voltage and high voltage power cables after testing we should use a discharge resistor stick to slowly bleed the charge off the cables themselves. Then we can solidly ground with approved ground devices. If we have been DC testing, the recommendation is to ground the cable at a minimum of 4 times the time that you actually had the test set connected to it. If you're performing VLF AC testing, then you can just reapply grounds after the VLF test set has been turned off, and the condition then can be put in electrical safe work condition. Other safe practices involve the minimum approach distances. We have high voltage testing being done AC and DC, so we're going to have these types of equipment energized with exposed live parts in the test area itself. So we do have to abide by the approach distances actually in the test area. The limited approach boundary is listed here for alternating current. If you look at the columns 1, 2, and 3 on the left side, this is basically the voltage level and the approach distances to movable and fixed parts for unqualified persons. If you look on the right side in the somewhat blue area, you'll see that there's a restricted approach boundary, and we also kept the prohibited approach boundary here in this presentation, because that becomes what's normally called the guard zone or the flashover zone. So even in a test area where you have all qualified workers, this prohibited approach boundary has to be adhered to, because if you get inside that, you may well actually create a flashover. Another issue with that is making sure that the test specimen is secured and is not adjacent to any grounded parts or anything like that would be within that prohibited approach boundary that possibly would cause an additional flashover. So this is voltage rated, so you go by the test voltage that you're actually using, and that gives you the approach dimension. This test area dimension has a couple of boundaries to consider. One of them is the limited approach boundary by unqualified persons to the actual voltage of the parts that we're testing or that we have live. The other issue would be a potential arc flash boundary. If there are other systems or other components in the system that we're testing that are adjacent to us and energized, then obviously we would have approach distances to live parts there to deal with, but you may well have to deal with the arc flash zone as well. One of the things that takes precedence over all of this is making sure we have enough room. If we're setting up a significant amount of test equipment in an area, then we have to have enough room to functionally use the equipment and to be able to move around in the test area too. So those are things that limit or dictate basically how large this test area may be. This is the approach distances to direct current voltage systems, and you can see it's similar in nature. And on the green side, we're talking about the limited approach boundary to either movable or fixed parts by unqualified persons, and that should have a bearing on our test area protection. And the other chart over here is the restricted by qualified workers using PPE are limited by this boundary, and then of course the prohibited approach boundary over here on the right would be for flashover protection. Okay, I separated this out as a separate discussion because it isn't. We have included it, but I wanted to make sure we covered this. This is a very detailed thing that's covered in 1910-269 Section O in the Transmission Distribution Generating Standard. And it has to do with the test operator in charge verifying before each series of tests that the test area is safe. And OSHA has listed at a minimum things here that they expect that we would look at to make sure the test area is safe for the test technicians as well as others in the test in an area outside the test area. We have all the barriers and safeguards are in place. Test area status signals if they're being used, and some companies use flashing light high voltage test signals, and we may in some facilities where they have test cages and high voltage test areas that have flashing signals as well. The test area power disconnects are available. We know where they are, and they're available to the test technician that would need to de-energize the test area. Ground connections are identifiable, that PPE is provided and in use and has been inspected prior to use, and that we separate our signal, ground, and power cables where we're using high current surge cables and we're using high voltage cables. The requirement here is that possibly signal or instrument cables would be separated from ground and power cables and not just all coiled together or twined together, which could cause spurious signals in the sensing circuits of some of the test equipment. OSHA mandates training requirements in several standards, but also in the industry consensus standards we find a significant amount of information as far as training requirements for qualified electrical workers. And this involves workers who work in the utilization equipment, i.e. things installed under the direction of the National Electrical Code, as well as things that are installed under the National Electrical Safety Code, which would be industrial and commercial power systems. So this qualified worker training requirement or training requirements also spills over into test area technicians as well, and testing technicians, whether they be in utilization and or power installations, either one. So the issue then becomes being a qualified person, number one, and then additional things that would be required because you are a test technician. So train prior to assignment. That's one of them, making sure that the individuals are trained at a competent level prior to assignment to the test area. They have received qualified worker training, so we're qualified to do the work that they're going to be doing, and understand the hazards and the means of mitigation. That's a short sentence with a lot of meaning. That the hazard identification in the workplace is a serious issue today, and being able to mitigate that hazard with proper work practices and procedures should be done prior to a level of PPE. If we can mitigate by work practice, that's a whole lot better than adding a different layer of flash suit to the issue. But being able to make that decision is the requirement here. Proficient in safe operation of the test equipment. I understand the equipment. I understand all the issues associated with the equipment. I understand the hazards involved in using the test equipment, and have demonstrated that, and also know when the equipment needs to be shut down and when to hit the e-stop. Trained in hazardous energy control for electrical work, which it means switching, clearing, locking, tagging, lotto or switching and clearance procedures, whichever we're working, whether we're working in utilization or industrial power, either one. So that's a significant thing. And in the testing environment, we find that a lot of issues actually occur because of verification and inappropriate switching and clearing. So that's where a lot of these things actually occur. Understand the requirements for test area protection to be able to identify what a safe test area would look like, how to set it up, what are the requirements, and how to maintain that. And then trained in the in-service care and use of all the PPE items that would be used in the system. So, and there are other training requirements, but these are the basic requirements that a qualified worker would have to work in a testing area. One of the big issues here is not only how to do the test, but how to analyze the data you get. So that might be a serious issue too, as far as training would be concerned. Okay, we've covered a lot of ground, and a lot of this is oriented toward cable and fault locating and testing in the field and those type of things, but applies to overall high voltage and high current testing regardless of where the tests are being performed. Electrical incidents do occur. They do occur in cable testing. We've had numerous fatalities where people have actually been thumped with a high voltage thumper. With a 1500 joule discharge unit, where it only takes about 6 joules of energy straight across the heart to cause heart fibrillation, a 1500 joule unit certainly has the capability of doing that. Most all of the test equipment that we use in medium voltage and high voltage power cable testing has the potential of creating lethal shock. So not only are you connecting it to a system out there that was energized and was the integral part of an operating power distribution system, we're actually simulating line currents and line voltages and things of that nature, which again puts us in a mode of being associated with live parts. The hazards of shock, arc, and blast need to be understood by anyone that works in the electrical industry. Being able to identify the risk associated with it and basically how to mitigate it with protective measures such as PPE and or procedures. And that's one reason why JHAs are so important. Technicians need to be trained in all the safe work practices for high voltage, high current testing in the field and test facilities. That we have numerous places to go look to get that information. The IEEE Yellow Book, which was later converted to a DOT standard, has 3007.1, point 2, and point 3. Point 3 is the Electrical Safe Work Program. The Electrical Safe Work Program is mandated. It has to be written. High current and high voltage testing would definitely be a part of the Electrical Safe Work Program. The NFPA 70B is another standard that has the electrical preventive maintenance program in it, and it does cover the technician training and the technician requirements for working in test areas involving utilization systems. So we have OSHA regulations, we have industry standards, and a lot of other information out there to pull from to write our safe work practices for high voltage testing and maintenance. A thorough understanding of and verification and grounding is required, and we still have a lot of incidents involved in the lack of proper verification of the system itself. Remember, you have to check all 3 phases. The meter has to work, so that's the other issue with it. And PBE grounds have to be engineered. They have to be designed based on the short circuit and coordination studies. So they have to be rated for the short circuit and the duty that they're actually going to be expected to have. Well, remember, we've already had a failure. We've already made an error because the grounds are now being operated or being asked to operate under a very severe condition, which would be maximum voltage fault energy. So we don't want another issue to happen and the grounds to burn up and cause a risk to the employees working there. We need to know how to conduct a test area safety check and to be able to understand when the test area has been safely set up, and that all the PPE items are there and everything that we need to conduct that series of tests has been validated. Okay, that kind of concludes our discussion.
Thank you, Mark. Thanks for that presentation. As a special offer and a way of saying thank you for registering for the webinar, ABO would like to offer you a 10% discount on the courses listed on your slide there. We've got 6 courses, starting with Electrical Safety for Utility, Industrial Facility, and the new NFPA 70E18 updated course, which we're rolling out as we speak. And also, this 10% discount would include the 3 cable courses that we offer: splicing and terminating, fault locating and tracing, medium voltage, and also the cable testing and diagnostics certification course that we offer. So at you'll receive a copy of this. There's a link there in this slide that you can go to register for these courses to receive this discount. You must register and attend before November 30th of this year, and we sure hope that you take advantage of this special offering. The next course that we have coming up here on the webinar, we're changing subjects a little bit to the substation arena, and the title of that course will be Substation Maintenance Load Break Switches. This will be October the 17th this year, 2017, at 1 p.m. to 2 p.m. Central Daylight Time. Our presenters will be Bob Fackelman and Greg Richmond. Both are substation instructors and curriculum advisors for ABO Training Institute. We think you'll enjoy that webinar, and we hope that you'll register for it as well. Now we'll go to your questions. Basically, the webinar has concluded with Mark's presentation, but we'd like to take the time now to answer any questions that you might have coming in. So what we'll do now is just take that time and answer a few questions, Mark.
Okay.
One question has come in: will we get a copy of this webinar? You certainly will. As I mentioned in the beginning, we will send out this webinar confirmation, and in that will be a link to the recorded webinar. So don't have to take a lot of notes. That will be coming your way, and also the link to register for our special offer will be in that slide. Mark, one of the questions that's come in is Corey would like for you to explain a little bit more about the Safe Work Practices program.
Okay.
What are the parts? How do you go about setting that up, etc.?
Okay, it was set up. If you go look at the ANSI Z10 standard, the ANSI Z10 standard establishes the requirement for a company to have a health and safety program. All organizations in the United States that employ people are required to have a health and safety program. And these are things like the hazardous energy control, confined space entry, all the environmental things, excavations, and all those types of things that affect their work. One of the requirements in that fairly recent ANSI Z10 standard is the requirement to have an electrical safe work program. If you analyze the hazards as required by OSHA, you identify the hazard in the workplace, then certainly electrical becomes a hazard, electrical shock, and arc flash. So the issue with work practices is defined as the electrical safe work program. You can find that in the IEEE 3007.3 standard. That provides the the guidance and the agenda and the makeup of the Electrical Safe Work Program. You can also find a brief model of it in the NFPA 70E. But in essence, it entails identifying the work procedures and the types of tasks that people do, and establishing the work requirements and methods of protection to protect them. So this Electrical Safe Work Program is audited. It has auditing requirements. It's required to audit. You're required to audit the program every 3 years. You're required to audit the application of the program annually by qualified workers. So it is a requirement in the U.S. You should be able to wrap your hands around a document, which is bigger than just a policy letter. This is most of the time it's a manual. It is the Electrical Safe Work Program. So hope that answers that question.
Mark, Josh, and I'll take this one for you. Josh wants to know what's the difference between this webinar and one of our ABO training classes. And I'll take that one. Basically, night and day. These are about a 45-minute presentation. We offer over 57 different courses. The 6 that you saw listed are 6 that we're offering this offer on. But the courses range from 1 day to 4.5 days. Very intense hands-on training. Labs up to 75% of the training will be addressed in specific courses. Anything from substation to relay to safety, we cover the bases, but it's literally night and day. These webinars are just a taste of the subject, but when you come here to the Institute and enroll in one of the courses, they're very intense and they cover the material very thoroughly. So I hope that answers that question. Mark, Bridget has a question here. I think it's related to the one that you just answered about the work practices program. It says, what is the employee's responsibility to the worker in developing these safety programs?
The employer's responsibility?
What is the employer's responsibility?
If you go look at the 1970 OSHA Act, that's federal law, in the duty section 5A and 5B, the requirement is that the employer has to identify the hazards in the workplace. They have to provide PPE, they have to apply procedures and those types of things and instructions to the workers. So, and they have to glean this from all the industry consensus and the OSHA requirements. So that's an employer responsibility. And the employer defined in the 1970 OSHA Act is the management team of the company. So this is not just a responsibility, this is a liability, this is a legal issue. So the employer has to glean from all the standards and regs the requirements that are going to cover their workplace. Then the other side of that is that OSHA didn't leave this out either. In the article, in that federal regulation, there is a second part. The second part is the employee's responsibility, and all employees are responsible for adhering to all the safe work practices and procedures that their employer has published. So it's a twofold thing.
Okay. Paul has a question related to the work practices and the employer's responsibility. How do you determine if someone is a qualified worker?
The qualification can only be established by the employer, and the employer has to have a process whereby individuals become qualified. Training is one thing. Classroom type training is really good to give the workers the information, to give them the hazard identification, how to recognize hazards, how to take care of PPE, and all those types of things. But the other requirement, though, is demonstration of skill. So a worker actually has to demonstrate that they can perform their task safely and that they know how to use PPE items and things like that in their workplace. So it's kind of a twofold thing, classroom and on-the-job both. And you have to have a process in a company that actually allows people to become qualified to do what they do. Mentoring and those type of things are important too, where you mentor with other qualified workers.
Mark, Brian Brian wants to know, what is the difference between 70E and 70B?
70E is the work practices standard for working on utilization systems. Let me back up a little bit. The NFPA 70 is the National Electrical Code. The National Electrical Code basically is the design safety code for all utilization systems in the U.S. and other countries too, but mainly the U.S. Working on utilization systems, because the 1970 code does not have work practices in it, the work practices were created by the NFPA 70E group that was formed at the request of OSHA. The 70E group has the work practices. This is the how-to work safely on utilization systems. Subpart S electrical standards and regulations are the OSHA requirements for working on those systems, but they basically give us the level of bar we have to jump over. The NFPA 70E gives us how to do that. Then the 70B, on the other hand, is how to maintain utilization systems. That's an extremely important document in the U.S. Since fire and fire loss is the #1 loss in the United States. That's why the NFPA is so involved in this, the National Fire Protection Association. So they have maintaining, installing, and working on, all covered in those three standards.
Okay, thank you, Mark. Fred wants to ask a related question, and I think in our last few remaining moments, we'll take this last question. The question is, does an 8-hour course, safety course, meet OSHA's requirements?
You can present OSHA's requirements to the worker in 8 hours probably. You could present them and say these are the requirements, but that would not qualify a worker. There's no a classroom really can't qualify a worker. A classroom and classroom instruction can be a big part of qualification, but the demonstration of skill has to be there. If a person sat through an 8-hour class and let's say they had a certain level of expertise that they had to gain, you could get the training in there that said these are the things that you have to know and be able to do, but you would still have to demonstrate that you can do them safely.
And who would you demonstrate that to?
You would have to demonstrate that to your employer,
So
your
it's the
supervisor.
employer's responsibility?
Typically it's the supervisor, it's an employer's responsibility to ensure that that person not only heard it, but they can actually demonstrate it. So it's a good thing to have the classroom training because a lot of that information doesn't get presented out there in the workplace. But the hands-on part has to be done.
All right, thank you, Mark. That looks like that's about all the time we have for the questions. We will answer the remaining questions that have come in via email. Someone had written in and said, how do we get our credit for this? We will send you a confirmation of this that you can submit for that CEU. We also offer a recording of this webinar session on our website, abotraining.com/webinars. That'll be up in the next couple of days. And again, you can come back and look at specific slides or share it with your colleagues. We'd like to thank you for joining us today. And remember, our next webinar is October the 17th. The subject is substation. We think you'll really gain a lot of knowledge from that particular presentation. We've got two top-notch training experts here to take you through that webinar. So from us here at ABO Training Institute, we'd like to say thank you and good afternoon.